Good.
Can you hear me?
Yeah.
Yeah. All right. So today I'm going to first present my solutions of the homework problems, and then continue on with the material. And so we're going to talk about special and general theory of relativity today. But first, homeworks. So the first problem was that you had a square. You had a gauge vector potential, right, which was given as and of course I forget to write. Yeah, okay, here it is. So it's ax, it's a vector, right? So it depends on coordinates. Ax equals some constant times y, ay equals 0, and az equals 0. So everything happens in xy plane, and so let's forget about the z coordinates. Nothing depends on it anyway. And let's draw that how that vector field looks like. So you see that it has only x component. So this is my x, this is my y, and its x component depends on y. So it looks like this. And what you needed to find out is the circulation of that field around the square of with the side a, little a, right? So that was the problem, and so the solution is the following. First of all, you have to notice that I didn't say that the sides of the square are parallel to x and y. So if it's not said, you need to assume that the square is somehow like this. Okay, all right. And I'm quite sure that majority of you didn't do that and just assume that the square is this way. Okay, that's actually not correct way to do that, because I didn't say that that the size is parallel to x or y or whatever. You should have considered the general situation. It's okay, we will not take too many points for it, but nevertheless, just please read read what is stated in the problem, not what you think it is. So now we need to compute the circulation. So how we do that? Well, we choose the direction around this loop, right? Something like this, and then we need to compute that integral of a dl. Right, so the dl is a little piece on that loop, and we need to compute that integral around the square. So the direct calculation is the following. It's actually, it's in some sense it is simpler when you don't have that nice symmetry here. So let's imagine that we have that little piece of our loop here. Right? So that little piece has its own coordinates x and y. So this is my dx. Now that length of that piece is dl. This is a vector dl, and there is that at this point it's very small loop, so there is vector a at the very same point. All right. So then what I see here? Well, I need to take the dot product. I need to compute the dot product at this point between vector a and vector dl, right? Because a has only x component, and this equals to ax times dx. This dx, right? Because this is dx is the component of the vector dl. The x component of the vector dl. Now ax equals by, right, according to the statement of the problem, times dx. After that, I should stop and think about what did I write here. Yeah. So now look at this. This is y times dx, right? So y is this distance. Dx is this distance. So what's written there is pretty much this area. Right? That makes sense?
Yes.
All right. So when I sum over all DL, let's say around from here to this point, what I will get then will sum of all areas. So I will get this area. Okay. So that will be this contribution. Now I will need to take this contribution. It will be this area, but with a minus sign because now dx is going to opposite direction. Then I compute this part, and it will be this area, right? Again with the minus sign. And then I compute this part, and it will be this area. And again with the minus sign. So plus with the plus sign now, because dx is pointing, L is pointing on the x direction, right? So if I compute those areas, what I will find is the minus the area of the square, right? Because it's this area plus this area minus this area minus this area. And so it's total area of the square. So the total integral will be equal to minus b times the area of the square, which is a squared. Okay? That make sense?
Yes.
So this is total circulation. And the next part of the problem was to compute what is a magnetic field here. So the magnetic field equals the curl of vector A. Vector field A, right? Well, you know how to compute curl. This is just determinant of Ex, Ey, Ez, dx, dy, dz, Ax, Ay, Az. You compute this determinant, and what you will find is this is minus b times Ez. Right? That's the curl of that vector field. And after that, you were asked to compute what is the flux of that magnetic field through the same square. Well, that magnetic field is a constant, so the flux is just the magnetic field times area. So the flux will be minus b times area, a squared. Okay. Does that make sense?
Yes.
All right. Okay, then let's move on. So the next the next two problems were just to get you familiar with all the Lorentz transformations and how they work. And so the first one was, so it's the second problem. The first question was to compute with which velocity a stick must travel along itself, and 1 meter stick would travel along itself. So when we measure it, we see that its length is half of the meter. So we take that one of the formulas which we derived last lecture, and it says that the length should that length which we measure must be equal to 1 minus v squared divided by c squared, the length which that guy and the other guy is measuring, the traveling guy is measuring. Now the traveling guy is measuring, the traveling guy is that meter stick, right? So this is 1 meter, and we measure half of the meter, right? So what you have here is that 1/2 equals 1 minus v squared divided by c squared squared. And of course, from here you just find what is that velocity is. So you have v squared divided by c squared, 1 minus equals 1/4. So that it means that the v squared minus c squared equals 3/4. Right? And so v equals square root of 3 divided by 2 times speed of light. And so, well, you can plug in numbers here. It's about 0.43 speed of light. Right? That makes sense?
Yes.
All right. So that was the first problem. The second problem was about the clock. And the story was that the clock which runs 1 day in the moving system of coordinates runs 1 day plus 1 second. Right, so what we see here is 1 day, A plus 1 second equals 1 day divided by square root of 1 minus v squared divided by c squared. That's exactly the formula which we figured out last lecture. So the first thing which you need to which you need to notice here is that 1 day plus 1 second is pretty much exactly the same as 1 day. That the difference between is very small. All right?
Right.
1 second on top of 1 day. So what it means is that this square root is almost 1. And it is, if the square root is almost 1, it means that this number v squared divided by c squared is very small. If that number is very small, you can use Taylor expansion. So this equal then it's 1 day times 1 plus 1/2 v squared divided by c squared. The accuracy is very good here. All right, and so now what you see here is 1 day. So let's write it 1 day plus 1 day 1/2 v squared divided by c squared. So you see that 1 day and this 1 day cancels out, and what you have is 1 second. 1 second equals 1 day times 1/2 v squared divided by c squared. So you see that v squared divided by c squared equals 2 times 1 second divided by 1 day. Right? And so the answer is this. And then you just plug number, how many seconds in 1 day, compute it, the square root, and then get the idea. And so the answer will be something like 5 times 10 minus 2 speed of light. Okay, that makes sense? Of course, you can do it more in more complicated way, right? You can translate everything into seconds here, everything into seconds here, get I don't know 1 second plus whatever number of seconds, and divide it on each other and do all this big numbers machinery, which I hate all the time, and you got pretty much the same result. The difference is some numerics which is beyond this accuracy. So Taylor expansion makes things easier to compute. That's one of the reasons to do it. But on the other hand, you see that even to get that little shift of time, just 1 second during 1 day, right? It's very small shift of time, something which you never notice when you measure time on your own, right? You still have to have very huge speed. I mean, this is 10 to minus 2, right? It's a small number, but it's multiplied by the speed of light, and speed of light is huge. So that speed is actually huge speed, right? It's beyond what we can achieve by far, right? So even that little once in order to gain 1 second, you have to travel. It is very, very large scale. Okay, that makes sense. All right, so next question was about the stick and the angle which the stick is making. So the story there is the following: that you have a stick, right? And this is my x direction, and it travels along x direction. And in its own frame of references, it has some angle theta. Now I am measuring, so it travels with velocity v. I am measuring that angle from my point of view. So what angle will I see? Well, and then of course you just need to use 2 coordinates, right? So there's y coordinates here and x coordinate here. And now for that stick, let's say that its length L, then its x direction, this length is L times cosine theta. This length is L times sine theta, right? And now I need to translate it into my own frame of references. Now y, because velocity is along x direction, y doesn't change. So in my frame of reference, Ly so Ly in my frame of reference, I don't know. Well, let's call this prime, right? It's moving system of coordinates. So in my frame of references, Lx equals Ly prime. The same thing here, L prime. So its length is L prime, right? And Lx in my frame of references equals Lx prime times 1 minus v squared divided by c squared. Okay. So what I have is this equals to the length of the stick, total length of the stick times sine theta, and this equals to length of the stick times cosine theta times square root of 1 minus v squared divided by c squared. Okay. So now, in my frame of reference, I observe angle alpha, and that angle alpha is such that tangent of alpha must be equal Lx divided by Ly. This is just definition, right, of tangent. And no, the other way, sorry, Ly divided by Lx. And so that's then which I measure, and all I need to do then is to take Ly divided by Lx. So I need to take this divided by this one. Right, so I see that this is tangent theta, and I divide by Lx, so it's 1 minus v squared divided by c squared. Okay, that makes sense?
Yeah.
So I see that this number is less than 1, so 1 over the number which is less than 1 is larger than 1. So the tangent which I observe is larger than the tangent which it makes in its own frame of references. Now, tangent is monotonically increasing function, so it means that the angle which I observe will be larger than theta. So in my point of view, that stick will sort of rotate a little bit. Well, it will shorten, it will also rotate. All right. So what I will observe is something like this. So Ly stays the same, right? So I will observe something like that. Okay. Now the message here is actually, well, it's a simple calculation, but there is a message here. When you observe real object, not just the sticks, like one-dimensional sticks traveling like one direction parallel to themselves or perpendicular to themselves. But you observe some objects, the angles of all different points on the surface of the object will also change. So it will translate into the fact that you will see different shape of the object. So whatever was shape was before, you will observe a completely strange shapes moving around. And in order to find out what was the shape in its own frame of reference, you actually need to redo some calculations with all the angles and then reconstruct it back from those formulas. So it's not only if some I don't know, some object is flying by with a speed close to the speed of light, you will see not only just shortening on that object, but also the shape will change, right? Because of the very same results. And so it can be look quite weird. In fact, I'm sure that I haven't checked, but I'm sure there are some games or some videos of how the world would look like if we travel, I don't know, along the street with a speed close to the speed of light. Right. Well, actually, I remember there was some game like that. I actually played it. So it's the world looks completely different. It's all the shapes change, all the colors change, and so forth. And I suggest you to find some videos or games and then just actually play it. It's fun. All right, any questions about it? Hello? Anyone?
It's just real weird to think about.
Well, yeah, it is weird. And that's why I actually think about it. I'm a professor here, right? I'm suggesting you to play video games. So I really do, because the world will look very weird. And so you should understand how weird it is. and it sort of opens your mind in some sense. You understand that it's things, the way you see things, it's not the way they are. It's in their own frame of references. So the different things look different in different frame of references because of the Lorentz invariance. And it's quite, I always find it quite, I don't know, fascinating to do. Actually, first I saw such a movie when I was a little kid. Back then it was on TV, there was some scientific program and they actually showed somehow how the world would look like. Now you actually have some games when you can like control things and like see how they look like. All right, okay, the next question was about that green light and red light. So the story there is that you have a red light, right, and you're sitting in a car and you're moving towards it, right? So from your point of view, the light, the red light is moving towards you. Right, you sitting put, right? I mean, you're always in your own system of frame of references. It's kind of schizophrenic to think that otherwise. So you're moving, and the light actually moving towards you. And because of the light is moving, there is a Doppler shift of its frequency. And so you ask how fast you need to move in order to see a red light as a green light, right? So then what we need to do is to go in Wikipedia or whatever in Google and see what is the frequency of different lights. So the light of the source, right? The source light, the frequency of the source light, it's a red light, right? Equals to, it's red. Let's call it red. Red. So it equals according to Google 450 terahertz. And the frequency, sorry, the frequency of green light, is 550 terahertz. The numbers are not very important. We are not going to be picky about what kind of, because it's actually, in fact, that our eyes are not so sensitive. We cannot resolve up down to single terahertz. So our eyes perceive that red light as red color. It's some range of frequencies. So it really the numbers here are, but it's in the right ballpark. So then what we need to do is to write the Doppler shift formula, and it's something which we derived last lecture, and it's this one. Now, in the lecture, when we derived it, we had minus here and plus here. But in the lecture, the light source was traveling away from us. Now it's traveling towards us, so the velocity changes sign, and that's exactly what happened here. And now all we need to do is to plug in numbers and compute it. What the numbers are. So if you now invert this formula and solve it with respect to velocity, what you find is that velocity equals f divided by f prime squared minus 1 divided by f divided by f prime squared plus 1 times the speed of light. And so you know the frequencies, and you substitute it here, and what you find is that this is 0.2 speed of light. And then I ask you to compute it in what is it, meter per second, and you just go to Wikipedia or Google and ask what is the speed of light in meters per second, and multiply 0.2 by meters per second, and the answer will be something like 0.6 times 10 to 8 meters per second. Or you can ask the same Google, what is the speed of light in miles per hour? Google knows everything. And so that, and multiply it by then. And what you will get in 1.3 times 10 to 8 miles per hour. Okay. So that's, again, that's a lesson. Don't try to use that excuse of Doppler shift when you're talking to a policeman if you're on the red light, right? Because then you get big fine for speeding. And if the policeman knows it. So, but nevertheless, that's the lesson which you can learn. And again, those games which I found when you like moving with speed of light, they actually do change the frequencies. So they change the colors of what you see also. So not only shapes will change, but colors of everything. And so what you observe is not the same color as what you painted. All right, that makes sense?
Yes, indeed. Yes.
Any questions? All right, good. I like it. It's good that you like it. Again, but just try to find those games. I mean, it's fun. It's something very unusual. All right, so now I'm going to proceed. Unfortunately, I have a lot of material today. I really want to go all through that. So I put a lot of links in the last version of my lecture notes. There are a bunch of links to Wikipedia pages about what I'm going to talk about. So if you want, you just go there and read. It's long paper, long articles there. They have all the details. I cannot go through all those details. But the first thing which I want to talk about is the Doppler shift. So as you can see, that color is changing. It depends on velocity, right? Now, so that's there's a special language which people use, especially astronomers use. So you see that when an object moving away from you, right, the frequency of light which is that object emitting is shifting to the lower frequencies, right? Lower frequency means closer to red. Red light has low frequency, blue light has the highest frequency of visible light, which you can see, our eyes can see. Then what is that Doppler shift in this situation is called red shift. So if you ever heard about somebody talking about red shift of different galaxies, what they actually mean is that the galaxy is going away from us. Right? And due to Doppler shift, the Doppler effect, the color of the galaxy, the color of the stars, it actually shifts towards red light, towards that. It's not necessarily red, right? It can be blue, blue star there, but it's not as blue as it's supposed to be. It's a little bit towards red. The frequency is a little lower, right? So that is called redshift. And if something moves towards us, then frequency which we see, which we observe, will increase, and it means that it will move towards the blue light, and that is called blue shift. So if you've heard about somebody talking about red shift or blue shift, that what they mean is that something moving towards away from us for red shift and towards us for the blue shift. All right, and this is a standard way to talk about the motion of the galaxies. People normally, those astronomers don't even bother in converting that shifts in velocity. They work with the shifts of frequencies as they are, because it doesn't make sense. I mean, to do it, it's the same thing, right? It's just some algebraic difference, algebraic manipulations with them. So, but also it also tells you that it's actually much easier to measure velocity than to measure, for example, distance. Right? Just imagine that the following situation, like real world, well, whatever real world means. So you observe a galaxy, right? The galaxy is a disk, right? And the disk is rotating. Let's imagine that we see that galaxy from the side of it. So what we will see is that disk like this, right? So that's how we see a galaxy. Well, I mean, it's normally sometimes has some inclination, so we see a little bit more over it, but it really not something which I want to talk about. Let's imagine that we see that disk. How do we know that it's rotating? Now, of course, we do know that because the galaxy is held together by gravity, and in order for the gravity for the galaxy not to collapse, it must rotate, the same as our solar system. Right? So theoretically, we of course know that, but it's never enough. Right? We need to measure that also. And but what you do then is what astronomers do. is actually, again, so now imagine that you try to measure the velocity of different stars. What does it mean that it's rotating? It means that this end of the galaxy moving away from us and this end of the galaxy moving towards us. But because the galaxy can move also as a whole, for example, away from us, right? They usually do. Then the speed of the galaxy which moving away on this end and this end will be a little bit different because it's rotating, right? That makes sense?
Yes.
Now imagine that you want to measure that velocity of rotation. Now, if you just go from standard to definition of velocity, you need to see how that star is shifting, that the distance to that star is shifting, right? And for some particular time, and divide the distance by time and see, right? And the same thing here, and then you'll see that they have different velocities. But unfortunately, we don't live that long. Those stars rotate with a lot, with the speed of rotation is quite large, but still not large enough for us during our lifetime to observe the shift of any star. And you can observe it on your own. That sky looks exactly the same for you as it looked to your parents, right? The stars are on the same positions. So you don't really, because they're so far away, then in order for them to shift their visible positions, they shift the angle at which we observe them, they have to travel very, 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 very long distance. And although the speed is not small, but it takes a lot of time to travel, right? Now, if you compare the sky right now with what the ancient Greeks or Romans observed, there are actually shifts, and it's possible to do that. I mean, they didn't have accurate enough maps back then, but nevertheless, people know that they saw a little bit different skies. The position of stars was a little bit different. So during 1,000 years, you can see the shift of the position of the stars which are closest to us. Now, stars which are closest to us are within our Milky Galaxy, and we are talking about different galaxies. That's completely different story. That's there is no way for us to really observe the change of position. That makes sense? But it turns out that because of Doppler shift, we don't need to do that. All we need to do is compare the spectrum of star here and the spectrum of comparable star on this end. And we see that they shift the spectrum, the spectrum of light which they emit. It shifts in here. It shifts going towards us, so it shifts to blue side in comparison to this one. That shifts a little bit more towards red, and this is a little bit more towards light. So we see that the comparable stars on this end and this end have a little bit different spectrum. The spectrum, the shape of the spectrum is the same, but it's just shifted. And because of that shift, we can actually measure directly the velocity of those stars. Just like that, right? So we don't need to observe them for a long time. We actually can measure velocity of objects of the stars much more accurately than we can measure the positions of the stars because of the Doppler shift. And so that's exactly what they're using to do. They're using to measure those velocities. And that's actually, there was a big surprise in there, because when they measured very accurately for many galaxies, they measure the velocity of rotation. It turns out that velocity of rotation cannot be explained by the Newtonian gravity or Einstein gravity. It doesn't really matter here because it's a huge object. Newtonian gravity works well in this situation. So they actually rotate faster than they should. All that galaxies which we can observe, they spin, majority of them, they spin faster than they should spin according to Newtonian gravity. And so that's exactly the origin why people talk about dark matter, that there is some more matter inside which provides additional gravity and which lets those stars to spin faster. And that's one of the major proofs of that the dark matter exists. There is something else which we cannot observe. Right? We can observe, in order to compute the speed of rotation due to Newtonian gravity, we need to know the mass of the galaxy. Well, how do they know the mass of the galaxy? Well, they just count number of stars and multiply by the average mass of the star. And but also they pretty much know how much gas around the galaxies and so forth. So those empirical numbers which work very well for all other situations. But in this case, it turns out that the total mass which we actually can observe cannot provide enough gravity for the stars to rotate as fast as they do. And the conclusion then is that there is some extra mass inside somewhere in the galaxy which we cannot observe. And that mass turns out to be quite huge. And it means that there is some sort of dark matter, something which exists there, which provides gravity, but which we cannot observe. That's what the word dark means. All right, so that's one. That was a big surprise actually for a lot of people. Now there are some other things about that Doppler shift. It turns out that if you look at the stars or the galaxies, and then you can sort of measure the distance to them. It's a very tricky business. We can only measure distance to the very close galaxies. Faraway galaxies, I mean, they look like dots. How can you measure a distance to a dot? And so the parallax which we have in our eyes, or even the difference between different position of our Earth around the sun, is that difference in position is not enough to see the difference in to measure the distance. Right. So it's then. But for the close enough stars and galaxies, for close enough galaxies, we actually can't do. So the story is that if our Earth is rotating around the sun, right? So it means that here is our Earth, and if there is something here, some galaxy which is close enough, and there is some very distant stars, then you see that when we observe that galaxy from this point, when our Earth on this point of the orbit, we will see that star to be on that position with respect to the distant stars, right? And when we are here, we see that the position of the galaxy shifted a little bit. And if we know that distance and we know that shift, so we know this angle, then we actually we can compute what is the distance. The same geometry. All right. So that's how we can measure the distance to galaxies. But if that galaxy is very far away, then it will not shift with respect to the even more distant stars or galaxies. So we will not be able to. We cannot measure directly the distance to the other galaxies. But we can measure for close enough distances. And what was observed then is that all the galaxies are moving away from us. Right? And moreover, the further they are, the faster they move away. Now we can measure the galaxy, the speed of the galaxy, right? And because of the redshift, they're moving away. It's a redshift. So we can measure the redshift of galaxies on different distances from us, and we see that the further they are, the more redshift they have. So it means that the further they are, the faster they move away from us. Right? And that's for everything. I mean, all the galaxies, well, there are some of them which are sort of strange cookies which move towards us, but well, it's a stochastic thing, right? But majority of them moving away from us. Now, it does not mean that we are the center of the universe, because if you look from any other galaxies to all other galaxies around themselves, they will also move away from some other place. If you think about it, it's actually quite easy to understand. What it means is that, think about you're blowing a balloon, right? So you have a balloon, right? And you put some dots on it, right? And then you expand it. You blow some more air in it and expands. And you see that all the distances increased between all the points, right?
Right.
But it means that no matter on which point you sit, and remember that end which is sitting and can only observe what's on the surface. From any position of that end, all the points will be moving away, because all the distances must increase. So no matter where that end is sitting, that end will see all the stars moving away from itself. What it means is the expansion. moreover, that end will see that the further the point is, the faster it's moving away during that expansion. So what it means is that our universe is expanding, and all distances are expanding. So no matter where you look from, you will always see that all the galaxies moving away, and the further they are, the faster they move away. Right? But it also means if there is such a connection between speed and distance, right, that if you know how to recompute one into another, observing our nearby galaxies, then measuring the speed of all the galaxies far away, we actually will know distance to them. Right? That's called Hubble constant. That's how you translate from speed to distance. And that Hubble constant allows us to measure speed, which we can do from Doppler shift quite accurately, right? and knowing that shift, knowing the velocity, then we know how far away the galaxy is. And that's exactly what astronomers do. That's how they know how far away every galaxy is. It's not only that, but if you listen to the astronomers, they will never tell you what the distance to a galaxy is. They will immediately tell you what the redshift of that galaxy is, because they measure, because of the Hubble constant, it's just a number. They measure distances by the redshift. Remember, redshift, right, means velocity. Velocity due to Hubble constant means distance. So instead of telling what the distance is, they always tell each other what the redshift of each galaxy is. And that's enough for them. I mean, that's how that's what they do. That's how they talk about the distances to different stars. So when they have some popular articles, they may mention what kind of distances, but when they talk to each other or talk to me, they always talk about redshifts of different galaxies. And it's up to me to understand the actual mean distance. All right, so that's one thing. Now, how you measure distance when the distance is so large? Well, the typical way to there are a few different ways to measure that, and one of them is just redshift. Just think about redshift as the shift of the frequency as you meter stick, as something which you measure the distance with. That's what astronomers do. But they also have some other more sort of intuitively easier to understand measures. Some of them called light years, and there are also some another unit which is called parsec. And I'm not going to explain what parsec is. I have a link on my lecture note. Just go there and read it. That's what I did yesterday. But light year is a distance which light travels during 1 year, right? Speed of light is known. Speed of light is constant. So if we say that we wait for 1 year and see how fast that light is traveling, then that's our measure of the distance. It's called light year. So just to give you some examples, our sun is 8 light minutes away from us. So it takes 8 minutes from about 8 minutes for the light to go from sun to the earth. Right? So that's the distance to the sun from us. Now I put it some other here. So the closest, I put some numbers here. The closest star to us is Alpha Centauri, and it's about 4.4 light years from us. So in order to reach that closest star to us, it takes light about 4.4 years. Okay. And okay. All right, so that's the distance to the closest star. Now, our galaxy, our Milky Way galaxy, you can ask what is the size of Milky Way galaxy, and that size, again, it depends how you count it, because it's not like it's sharp, right? It's the stars are going more and more sparse away from each other, and so it can be estimated to something like 100,000 light years. So in order for the light to go from one side of galaxy to the other, it takes about 100,000 years. Okay. So that's typical astronomical sizes. And now our galaxy, it has a lot of small satellite galaxies, which the distance to those galaxies is actually smaller than the size of our own galaxy. So that's very small satellite galaxies which are around our Milky Way. And the next large galaxy, which is the closest to us, to the Milky Way, it's about what it's 2.5 million light years away from us. Okay, so light needs to travel 2.5 million years to reach that Andromeda. That galaxy is called Andromeda. So you can imagine that it's pretty much no way for us to fly there, unless we find some other physical principle which allows us to sort of skip that distance. But actually, with the case of Andromeda, we don't need to, because in a couple of billion years, the Andromeda galaxy and Milky Galaxy will collide with each other. They're on the straight path for collision. So we just need to wait a couple of billion years. All right. So it's and they will come to us. So that's typical astronomical distances, which and again, this is just the closest ones, right? So the very far away stars, they're about 10 billion light years from us. Okay. Now, I also want you to understand that it takes 2.5 million years for the light to reach from Andromeda, which light was coming from Andromeda, to reach us, right? What it means is that when we observe Andromeda, we see the light which was emitted 2.5 million years ago. Right? Well, that's how much time that the light took for travel. So it means that when we observe some other stars, the further the star away, the earlier we observe. So what we observe is not the present state of all those stars. We observe the past. So and the further you look at, the earlier life of the universe we observe it. So that's why astronomers really want to look at very far away stars. Because then, if you know what's going on there, if you can measure some processes which are going there, on that far away. That means that we are measuring processes which were occurring during the formation of our universe. So we can look deep into the history of our universe by looking far. And that's why one of the reasons why astronomers are interested in building bigger and bigger telescopes. Because the bigger the telescopes, the more light it can collect. The more light it collects, the smallest objects, the faintest objects we can observe, and those objects are exactly the most far away galaxies which exist in our universe. And observing them, we observe the past of our universe. Actually, in fact, the earliest thing which we can observe is called microwave background radiation. It's a microwave. It's not light anymore. It's so hugely Doppler shifted that it's not light. It's a microwave. It's the same frequency, the same as in your microwave house. So there is that microwave background radiation which comes from everywhere, from all the directions, and that microwave background radiation was emitted in the universe at the first time when universe became transparent. At the very early stages of our universe, it was so dense that it was actually not transparent for light. Now, then it started to expand. Well, it was expanding before. It continues to expand, and eventually there was some phase transitions which happened to that universe, for our universe, and it becomes transparent to light. And we still can observe that light. But because it's so much Doppler shifted, that it's not light anymore, it's a microwave, And that's exactly what microwave background radiation is. And we can observe some peculiarities of that microwave background radiation, how it's distributed in different angles and so forth. And from that, we can sort of try to figure out how our universe looked like at the first stage when it became transparent. Right? That makes sense?
Yes.
All right. Again, so if you're interested more in those things, please go to Wikipedia and read it. And they have Wikipedia in this case knows more than I do, and those subjects. And that's not really my specialty. I just heard some colloquium talks in our department about those things. Well, I read books also. So anyway, so that's fascinating stuff. I just want you to understand how far we went from observing, currents and charges, Coulomb's law and Ampere's law, and so forth, and going through Maxwell equations. We figure out that there must be Lorentz invariance. Looking at the Lorentz invariance, we find out that there is Doppler shift for light, and now the Doppler shift can give us another view of the universe which we see. All right, so I think it's the whole progression is quite beautiful, how things develop. All right. So now, but so far, what we talk about is just the kinematics, how to go from one frame of reference to another. But that's not the only thing which we need, right? We also need to know what is momentum is of particles which are traveling with close to the speed of light, and we also want to know what the energy of those particles are, and so forth. So that's exactly what I'm going to talk about as this part of the lecture. And it's so there is some formal and strict way to do that. It's quite complicated, and it would take a long time to do. So I will cut some corners. What I'm going to talk about is not precisely rigorous, right, but it works. So it's if you need to learn more, I mean, you have to take the proper class on it. So let's do the following. Let's say that we have some particle and we apply some force to it. And let's at first just forget about everything and say that if we have that particle, right, then after we applied force, the particle is moving some distance, and the energy its energy will increase by force times dx. Right? Dx is the distance which the particle shift and the force which we apply to it. Right? So this is work which we've done, and this is the change of the energy. All right. So that's standard. And on the other hand, its momentum will change by force times the time which it took for us to apply that force, right? Or that distance dx. This is just the same thing which you remember that Newton's law is P dot equals F, right? So this is dP over dt equals F. So from here, I just go there. Okay? Now I look at this, and from here, I see that dx equals dE divided by force, right? And dt equals dP divided by force. Okay? Now let me multiply it by c, right? And then square this and subtract this one. This will be the interval between this point and this event of my process. So what I have is ds squared, the interval between those two observations of particles here and here, equals dE squared minus, no, the other way around, sorry. So the interval equals c dt squared minus dx squared, right? Remember that? And using dx and c dt from here, what I find is that this is c squared dp squared minus de squared divided by f squared. Right? That makes sense? All right. So, but that interval that interval is the same in every frame of references, right? So what I see from here then is that the dE squared minus C squared dP squared must be constant for every frame of references. Okay. So now, if it's a constant, let me find out what that constant is. So to do that, what I see is that my energy, let's imagine that my energy is small, so D is pretty much the same as energy. So that energy equals some constant plus C squared, P squared, and square root. Okay. Now let me imagine that momentum is very small. I want to translate that to the standard Newtonian mechanics, for which I know the answers. How momentum and energy is related to each other. So I want to assume first that this is a very small number. If it is a very small number, I can use the Taylor expansion, and it will tell me that this is square root of some constant, this one, right? That's the first term of Taylor expansion over here. Plus 1/2 C squared P squared divided by the square root of the same constant. Right? Now this is a constant, and energy is always defined up to a constant. So I can in normal Newtonian mechanics. So I can always throw it away. But then this must be my kinetic energy. But the kinetic energy in Newtonian mechanics is P squared divided by 2m squared, by 2m. M naught, let's call it M naught for now. For reasons I'll tell later. Right? So I need to compare this one with this one, and what I see is that this constant must be equal to M naught squared times C to the fourth. Right? So if I substitute this constant M naught squared divided times C to the fourth, I see that C squared cancels this C squared, and M naught squared, I take the square root, and I get M naught. And I get exactly the same formula. So I recovered again the Newtonian mechanics. Right? That makes sense? So what I have here is, instead of constant, is M naught squared C to the fourth. Okay? Or in other words, what I have is that energy of a moving particle equals to M naught squared C to the fourth plus C squared P squared. Right? So this is instead of kinetic energy. So in Newtonian mechanics, the kinetic energy was P squared divided by 2m naught, and in special relativity, energy equals for particle of mass m naught, rest mass m naught. That's what it, the energy equals the square root of m naught squared C to the fourth plus C squared P squared. Okay. Now, that's actually quite surprising formula because it's, first of all, plus and minus sign which is supposed to be here. I just wrote the plus sign because I want energy to be positive. But it turns out that in quantum mechanics that minus sign is also very important. And it actually provides us with antiparticles. The antiparticles which we have like you know, antimatter. If you watched Futurama, you know what antimatter is, right? So it's exactly that minus sign here, which is emitted in the mechanics, but we must be very careful with that in quantum mechanics. All right, so that's one thing here, and the second thing, you see that when momentum equals 0, that energy does not equal to 0. And we cannot disregard it as just some sort of constant. That's a very strict formula. So what we see is that when momentum equals 0, my energy equals m naught c squared. So the energy still exists, even if the momentum is not is zero. So this is the rest energy of any particle. Any object will have that energy associated with that mass. Okay. This is, by the way, not the formula which you see on T-shirts. In T-shirts, you see it without zero here. I'll come to that other formula in a second. This is just the statement that we have to associate the energy with the rest mass. That's all. All right, but it doesn't change so far. It's just the rest mass of any object. So that's but again, so this is our kinetic energy now, right? Is it understood? Is it clear?
Understood.
Yeah. So it's energy as function of momentum. Right? Energy as function of momentum is a Hamiltonian. And if we have Hamiltonian, we can write Hamiltonian equations of motion. Right? This is now our Hamiltonian because it depends on the momentum. And the Hamiltonian equations of motion tell us that P dot equals minus d Hamiltonian. Hamiltonian is now our E divided by differentiated with respect to x, the coordinate, and x dot equals dE over dP. The energy must be conserved, so Hamiltonian, the mechanics must be Hamiltonian mechanics, and then we can write Hamiltonian equations of motion. Now, if you write it, so the first equations out of those tell us, because that formula, there's no x here, it does not depend on any coordinates, it tells us that P dot equals 0, all right? So it means that momentum is conserved, something which we expected, right? Because it's conserved in Newtonian mechanics, and the origin of that is the translation invariance of our space. Special relativity does not break that translation invariance of the space, so momentum still should be conserved, and momentum is conserved. Right? Now, from this one, on the other hand, we know that this x dot, right? So this is velocity. This is the derivative of position with respect to time. This is exactly velocity. So we can take that, we can then write it that velocity equals, and now what we need to do is to differentiate with respect to momentum. Right? And what you find is that it's c squared p divided by the same square root. M naught squared c to the fourth plus c squared p squared squared. Right? That's just a derivative. I just differentiate this function with respect to this letter. That makes sense? All right. So now from here, you see that I have now connection between velocity and momentum. So I can invert it and just solve it with respect to momentum. So what I need to do, I need to square the both parts of these equations and do some reshuffling and find out how momentum depends on velocity. So the answer will be the following. I'm not going to do that, perform that simple calculation. You can do it on your own. So that momentum equals m naught v divided by square root of 1 minus v squared divided by c squared. All right. And again, that's just a solution of that with respect to p. And again, what I can do, I can say that what if my velocity is small? If my velocity is small, v squared divided by c squared is very small. So the square root of the order of 1, so it's pretty much 1, right? And what I have is p equals m naught v, right? P equals m naught v. This is your standard Newtonian momentum and velocity relationship. But nevertheless, that's not correct, right? That's not exact. When velocity becomes large, then there is that square root which will change it. Now, notice that when velocity becomes close to the speed of light, momentum actually goes to infinity. Right? So velocity is still finite, but momentum goes to infinity. It becomes larger and larger and larger and larger and larger. Right? Does that make sense? All right. So, but now I can do it even the other same. So I said that this kinetic energy. It's in reality this is Hamiltonian, right? Because it depends on p. Typically, kinetic energy, we say that kinetic energy is how energy depends on velocity. All right, and so I can now do that. I can just take this P and substitute it back here. All right, and what I will find is that energy will be equal to m naught c squared divided by square root of 1 minus v squared divided by c squared. Okay. So again, this is just taking this substituting here. Okay. Does that make sense?
Yeah.
And now I do the following trick. I mean, this is just a trick of convenience. It has no real, I don't know, reason to do that. It's just convenient to do it the following way. So let me write it the following way. That I say that this is my effective mass. Right? And then what I say is that this is some mass times velocity. Right? The very same formula as before, as normal Newtonian mechanics, but now my mass starts to depend on velocity. And what I will find is that this mass equals rest mass divided by 1 minus v squared divided by c squared. So it is not, momentum is going to infinity when velocity approaches speed of light because mass is divergent, right? So when I try to move things faster and faster, they look to me more and more massive. That's what this interpretation tells me. But this is just interpretation. But now, if I take that mass and use it over here, what I will find that energy equals mc squared, right? And I cannot believe that there is anyone in this class who never seen this this formula. And so it tells you that, if you call this mass, and this is a very natural thing to do because now it will look to us as mass because of the momentum. Remember that momentum is you apply force, right? And that's how much your momentum is increasing. So now you apply force, you try to accelerate things, and instead of acceleration, instead of changing velocity, your mass is changing. And it looks like it takes more and more and more force in order to achieve bigger and bigger velocity because the mass is divergent. So that's very natural thing for us to intuitively sort of a little bit clearer to imagine it this way and use the full formula. That there is a mass which diverges with when we approach the speed of light. And that's why we cannot overcome the speed of light in this sense. We try to push it, we apply force in order to push it further, faster and faster. But instead of increasing velocity, it will start at some point increase its own mass. And it will require even more force and more force to give it a little bit increase of velocity. And eventually it will require infinite force. So that's why one of the interpretation why we cannot go faster than the speed of light. But in reality, it's just like, there is no speeds more than the speed of light. That's it. And that's just an interpretation. All right, it's not like we can apply any force. It doesn't exist. The velocities do not exist beyond speed of light. So that's basically what it means. That formula, in fact, that E equals mc squared is actually the only thing it means is this one. But it also tells you some sort of interpretation of it, some uses of it. Sorry, not an interpretation. So now you can see that energy, according to this, and mass are actually related to each other, right? So it also gives us a tool to measure some things which we cannot measure otherwise. And the example of such thing is a measurement of a binding energy of a nucleus. There are some other examples, but I want to use this one. So remember that this is rest mass, and this is the mass which we measure when things are moving with velocity. All right. So what is the binding energy of a nucleus? Well, nucleus consists of protons and neutrons, right, in an atom. And binding energy is what it means is that how much work we need to do in order to take this nucleus and separate it, all the protons and neutrons far away from each other. We can do it different way. We can pick it one by one, or pick one shell, move it around. This next shell, move it away from there. It actually doesn't matter. It will be the same thing because all the forces are conservative forces, and it means that the total work will not depend on which process you choose. It depends on the initial state and the final state. Initial state is the nucleus, and final state, then all the neutrons and protons are very, very far away from each other. Right? And how much work we need to do is exactly the binding energy of that nucleus. Right? That makes sense?
Yes.
It also, if you have that bunch of neutrons and protons, when they combine back to a nucleus, that's how much energy they will release. Right? Because energy must be conserved, they must dump it somewhere. They usually dump it in some heat. Well, there are some processes, we need to consider the processes more precisely. But nevertheless, that's the energy which we can extract by combining them together. This is called binding energy of nucleus, and we can actually measure it. Without, you understand that in order to, by definition, in order to measure it, we need to take like every proton and move it away, right? That's pretty much impossible. Well, we don't know how to do that. But nevertheless, we can measure those things because of the binding energy, because of the relation between mass and energy. Because in reality, the only thing which we need to measure is the mass. So imagine that we measured the mass of that nucleus, and it gives us M, capital M. Now we know that there is some number of neutrons N and some number of protons. When they are far away from each other, right? They're just free particles moving around. We know the mass of each. We know the mass of a proton and the mass of a neutron, right? So then the total mass of the constituents here is the number of neutrons times the mass of each neutron plus number of protons times the mass of each proton, right? Right? But this mass and this mass will not be the same because the binding energy translates to the difference in masses, right? So what it means is that if you now subtract here the total mass of the nucleus, which we can measure. I mean, we don't need to break up that nucleus in order to measure its mass. I mean, it's some experiment. It takes some experiments to do that, but we can do that. And if you multiply it then by c squared, this will be our binding energy. Right? And then we can do different tricks with that, with that consideration. We can say that what if we have a nucleus and we separate it on two different parts, right? Do we need to do the work or will some energy be released during the process? And the only thing which you need to do is to compare the mass of the original nucleus and the masses of the resulting nucleus when you separated them, right? And looking at those numbers, you see that if the original mass was larger than the sum of two masses which appeared before, then it means that when we separated them, some energy must be released, right? Because that extra mass should be converted to the energy. And then we know that if we do that, if we split a nucleus in two parts, then we will have some additional energy which we can use. And that's exactly what nuclear reactors do. Or it can be the other way around, right? So that if we separate some nucleus and the results have more mass than the original, it means that we need to do the work to separate them. But if we need to do the work to separate them, it means that energy will be released when they combine, right? And that's what the thermonuclear reaction is doing. And fission and fusion, I could never remember which one is which. So those two different ways they both exist, and in fact, if you consider the heavy and heavier masses, heavy and heavier elements, then the boundary is about something around iron. So before iron, lighter than iron elements, they will release energy when you combine them, and heavier than iron nucleus will release energy when you separate. Okay, so that's why uranium is much heavier than iron. So we separate that uranium and get the and getting some energy out of it. Oh, sorry, give me a second. Okay, all right. So that's how we know how to get nuclear energy. From that, why is this relativistic thing is actually connected to the nuclear energy, which we can use and as a source of energy, or to make a bomb, but it's a different story. All right, does it make sense? Sure. Well, of course. I mean, what does it mean, a mass? It exactly means that one. You try to accelerate it, and its velocity does not increase that much. You pump energy into the kinetic energy, right? With some big, like whatever is the electric field which is there, right? But the velocity does not change much. I mean, think about it. If you're 99.999% of the speed of light, any increase of velocity, any increase of velocity will increase that mass hugely, and the velocity itself will not increase that much because you're already at the boundary. So you try to accelerate those particles more and more and more, and the speed does not change. So the next homework, you have exactly this problem, and because of exactly this question. So that's why those high energy people, they never tell you what the velocity of the particles are. Try to ask them. They probably don't even know. Because for all what matters, for all what we can measure, the velocity is so close to the speed of light that we actually cannot distinguish between them. We don't have enough accuracy to measure the velocity itself. What they always tell you is what the energy is of those particles. Now, but velocity is the same for all the particles. The only thing which we do, we increase the energy. But so it means that we increase in the mass. All right? So that energy, that high energy, that energy which they're talking about is exactly the mass. Right? But velocity, again, velocity doesn't change when you accelerate particles. Kind of weird, right? You accelerate particles, velocity doesn't change. All right. Well, it changes just a little bit, unobservable. All right. So that's pretty much all about special relativity, which I wanted to talk about. And I have 15 more minutes, and I'm going to explain the general theory of relativity in 15 minutes. As you can understand, probably I will not be able to do that because it normally takes a couple of years. And but I just want to point out where it comes from and how it's developed and what it all means. The mathematics of it is more complicated than anything which we have done here, and it does require some work to actually be able to understand what the hell those people talk about. But the origin of that, nevertheless, is quite simple. As usually, in the big progress in physics always come from some simple arguments. If the argument is too complicated, it's probably wrong. But here we have a simple arguments, and those are arguments the following. So I want to consider two different sets of strange things. All right. The first one is the following: something which you actually know already, but probably never thought about it. So we have Newton's law, F equals ma. All right. You see that everything comes back to the origin, right? We also have Newton's gravity law, right? That F equals G mass, one mass, the other mass, and divided by the distance between them squared. Okay, those two laws they both have masses here. right? Does that make sense? Yeah, you know this, right? Now, but think about it. Those are completely different situations. There is nothing which connects this one to this one. In this situation, it's free particle, right? You apply some force to it, and you measure acceleration. And the coefficient between them is called mass. That's all. Nothing else. Right? So it is experimentalist who applies force and the particle of mass. Now, so, but what you can see from here, that mass, is that if you apply the same force, and we can always do it without even knowing what force is, right? So you just you have your particle, you have a spring, and you push the spring against the particle such a way that the spring is shortens the same distance, and you keep that shortening of the distance all the time. That will be constant force applied to this object. Now we can do it with another object, this and apply exactly the same force, but just shrinking that spring the same way. So we don't even need to know to measure the force in order to do this kind of comparison. So we have here's one particle with mass m. We apply force. We find the acceleration, right? The acceleration you just measure the distance we start. Now, if we double the force here, double the mass here, but keep the force the same, right? We will observe that acceleration is half of the original acceleration, right? And we can measure all of this. That's one experiment. The next experiment is I go here, I have two masses. One is big one with capital M, another is small m, right? Nothing is accelerated. I just keep them on some positions, distance r from each other. All right? And then if I double mass, the force is doubles. Right? If I put twice mass here, the force will double. So notice that it's the same mass as here. So what I say here is I apply the same force, the acceleration halves, then I take that next object, that new object, and put it in here. Then force will double. Right? For any objects. How do they know about each other? That's completely different experiments. Now notice that it's not necessarily so. There are some other forces, like Coulomb's law. Coulomb's law tells you that F will be equal to KQ, capital Q, divided by R squared, right? So if I double the mass here, that force will not change. Because I need, for that force to change, I need to change charges. So how come that charge, which is here, right, it plays the same role, is exactly the same as completely unrelated thing in how particle responds to a force? Why are they the same? In reality, what you need to do is to say that this is completely different thing. It's called gravitational mass. This should be called inertial mass. This one is measuring in this experiment, and they should not know about each other. Yet they do. Right? That's a huge surprise, if you think about it. It's completely two unrelated experiments, completely two unrelated phenomena. Moreover, we know that the forces when it is not so. So you see that it tells us something is not quite understood. It tells us that gravity and inertia somehow related to each other. Right? Otherwise, there is no chance for those two charges here and the response here to have anything to do with each other. The same as Coulomb's law, right? And this inertia mass. They know nothing about each other, right? So what it means is that Coulomb's law is not related to inertia, but gravity must be related to inertia. Right? That makes sense? All right. So you see that
Yes.
you know both of those laws, right? And you know the consequences. The consequence of the fact that inertia mass and gravity mass are the same is why all that acceleration of free fall is a constant for all objects. Right? So we started, you usually start studying physics from this assertion that those are two things the same. Now try to explain it. Why would they be the same? Just because that professors use the same letter to denote them. Well, all right, never trust your professor. Okay, so that's the first thing. Relation between inertia and gravity. The next thing, which also, I remember that when I was studying physics, like in school, high school or something, it always bugged me that one of the Newton's law, I don't remember, I think it's first law, third law, I already forget. So it tells you that all frame of references, all inertia frame of references are the same. So what it means is that if you have one frame of references and there is another frame of references which moves with a constant velocity with respect to the first one, then all the experiments will be the same, right? But how do I know that the first one is not accelerating? Now, if I'm an empty space, and let's imagine that my frame of reference, myself, right, and my own frame of references is accelerating for some reason. I don't know why. Right? Maybe Newtonian mechanics is not correct and everything is accelerating. That's it. Right? So if my frame of reference is accelerating, then every other frame of reference which has constant velocity with respect to me will also be accelerating. And then I don't really know what the Newton's law talking about. So what is that first frame of references which is not accelerating? Right? No, that question actually has an answer. And in order to understand it, I want you to think about two different experiments. So there is a box, let's say an elevator, whatever, doesn't matter, a box, right? And you are sitting right here, almost standing, right? And you feel that there is a force acting on you, right? There is a weight, you push it against the ground, right? And let's imagine there is no charges or whatsoever. So what would be your conclusion from here, from that fact? Or, exactly, yes? So there are two different ways to explain that. That there is a earth in beneath you, right? And it pulls you down with the gravity. Or that your box is accelerating up. And there is nothing. And you're in free space. Okay? And because of that gravity, inertial mass, and the gravity mass are exactly the same, you will never be able to tell the difference between this situation and this situation. Right? Because they are the same, right? So it means that because of the acceleration, the force which will push you down will be exactly ma, right? And if you're accelerating with acceleration g, right, with acceleration of free fall, the force which will be pushing you down is mg. If you stay in here, the gravity is applying force which is also mg, and there is no way to tell this force from that one, because the masses are exactly the same for all objects. The inertial mass and the gravity mass, right? So that there is no difference between that you being in a gravity and accelerating. Now, if you can look outside, but remember that everything is dark, there is no light, so you actually cannot see the Earth itself, right? So, but you can look outside. Then you actually can tell it, because if you look at every object far away, right, then everything accelerating, so that object will also feel some force with respect to you. Some distance objects which are very far away. In here, the distance objects which are very far away will not feel that pull down, the gravity. The gravity decays with distance, and this inertial force does not decay with distance. It's a constant. So the only difference between them, between the gravity and the inertia, is the behavior at infinity. Very far away, gravity is decaying, and inertial force in an accelerating frame of references will not decay. But there is no other differences, right? So then what we need to do, we need to assume that this is our situation, right? We don't look at outside, we look only locally. And then we do that trick and make that Lorentz transformations in such a way that I'm moving with accelerating frame of references. So that my Lorentz transformation should change all the time, right? But that will be local. And then I look locally on that Lorentz transformation. And remember that Lorentz transformation gave me metric for the space. That interval which we use today, c squared dt squared, sorry, dt squared minus dx squared, right? That interval, it should provide me with a metric. If I now in accelerating frame of references, that metric will be different. I will observe different metric around the space. And if I now compute how that metric looks locally in my space, what I will see is that it will describe a space. Metric describes space, right? It describes space-time which has a curvature. It's not flat. Pythagorean theorem does not work. The sum of angles in a triangle is not 100 degrees, right? So, but then I'm saying that this is indistinguishable from the gravity. So the conclusion then must be that the gravity is not a real force. The gravity, what it does, it makes our space not flat. It curves the space, and the masses are the sources of that curvature of space-time. I have to emphasize this. This is not just space which is curved; it's a space-time which is curved. All right, but time is also involved there. So, and that's exactly the origin and the reason for the general theory of relativity, which that's exactly the statement of the theory, which tells you that masses, what they do, the gravity is not really force. The gravity, what it do, it changes geometry of the space around itself. It makes it curved geometry. It's not flat anymore. It makes it curved. And that's exactly what Einstein did. He wrote that statement mathematically. He was a very good mathematician, in addition to being a very good physicist, incredibly good actually. And and then he also, there is also another requirement for that theory. When masses are small enough and distances are large enough, then the theory should go into Newtonian mechanics, into Newtonian law of gravity. Because we know that it works, right? So it must work for small enough masses. And so he wrote a theory of a mathematical expression for that gravity, which satisfies those both requirements and of gravity, and it actually works. We can check it. So the space-time metric is curved. Right? What it means is that if you shine a light past a massive object, the light must bend, right? Because it's moving in a curved space. And when light is bent, it's actually visible. You can observe some very heavy star. We are sitting here, and if there is some other star which is far away, somewhere here, all right? So if you observe some very large object, then what you will see is that if that star is very close to that object, then the light will bend a little bit, right? So the star which is behind, really behind the object, you will still be able to observe because it's light coming from here. It will look like it is here while it is shifted a little bit. That can be observed even due to gravitational force of our sun. And usually it's very difficult to do because sun is very bright, so it will obscure all the observations by very huge brightness. But when there is an eclipse and the sun is covered by moon, then we can. It was actually observed that when sun is moving around, well, actually we moving, right? But then some stars will start to jump at the edge because they're not they sort of start to accelerate a little bit. It's visibly looks like accelerating because the star is here, but all of a sudden it appears over here. Right. So that's one reason. That's one way. The other way is to compute corrections to orbits of different planets in our solar system, and especially that's important for Mercury. It's close to Sun, so it feels that gravitational force the most. And it turns out that there are corrections due to general relativity. There are corrections to the orbit of Mercury. It can be measured, and it has been measured. And it was one of the experiments which showed that Einstein is right. But Einstein's theory also had a lot of other things which were not put inside there. If you look at those equations and analyze them, that what you will find is that if mass or density rather, if is large enough, so that very massive object was compressed somehow to a small volume, then it actually turns into a black hole. And black holes are things which light cannot escape. Remember that in order to escape our Earth, we need to have, what is it, about 11 kilometers per second velocity, right? In order to escape Earth's gravity and go very, very far away. And so eventually, if you compress that massive object dense enough, then the escape velocity will be equal to the speed of light. And it means that the speed of that light cannot escape that object, and such object is called a black hole. Right now, the very same effect of bending the light can be used also to make a gravitational lensing. Right, think about it. If I have this situation, let's imagine that this is some sort of galaxy, right? And I'm sitting here. There's a very distant star over there. So the light can go like this, or the light can go like this around that galaxy, to me, right? But that's exactly the lens, right? So I have a telescope, which is a focal length, which is like distance to the next galaxy, right? And then I can observe those very, very far away stars. And it's actually done. It has been done. Such effects have been. It has been observed. You can check Wikipedia. It's called gravitational lensing. Right? But there is also one more thing about it. Sorry, I have to go a little bit over time. The fact is that it is space-time. It means that there is time derivatives will be there always, right? You have to write differential equations. The result of Einstein theory is some sort of differential equations. They're very complicated. I don't want to write them down. And but those differential equations will have derivative over time, because time and space are they play the same role in relativistic theory. But from our point of view, what it means is that gravity has its own dynamics, and it must, because think about it. If I do an experiment, right, and there are two masses, one of them here, one of them here. And there is attraction force between them, the gravity force. Now, if I move that mass somewhere here, that force must change. Right? It must at least direction. Right? But let's imagine that I move that mass very quickly here. Then it must take that change of the force must not be immediate, because that action of that mass from one mass to another mass must travel from this mass to me in order for me to observe that there was some changes. But nothing can travel faster than light, right? It means that when I move something very quickly, the gravitational force must be disturbed, right? And that disturbance of the gravitational force must propagate. The gravitational field must propagate, right? In order to reach me eventually. And so what it means is that there must be some gravitational waves due to the theory of relativity. There is no way around it. And those gravitational waves actually do exist, and they can be observed. And they have been observed a few years ago for the first time. The experiment there which observes them is very, very close to that Michelson-Morley experiment with diffraction of two beams of light in different directions. And but it's much more precise. Those people actually, the experiment is absolutely amazing because what they do is beyond belief. They actually have those mirrors which about, I don't know, very far away from each other. I forget what the distance is, but very far away from each other. And they can control the distance between those two mirrors, which are far away from each other, with the precision better than the size of one atom. Right? So if you think about it, it's pretty much impossible because you have temperature, and it means that all atoms are moving around. Right? So what is the precision? How can you move the precision? Well, that's why they have to cool it down, those mirrors, but they still can keep that precision, and they can measure the distance, the change of distances in such precision. And they have, but right now they only can measure some very huge disturbances of the gravitational field. And the typical situation is when two black holes collide somewhere in the universe. If two black holes collide, it's a huge gravitational waves, huge energy goes to gravitational waves, and they reach us eventually. They travel with the speed of light. So the black holes collided a few billion years ago, but we just see it, but that disturbance just came to us. And they actually was able to observe that disturbance. And they also observed some neutron star colliding with black hole, something like that. But if you think about it, if you can make those experiments better and cheaper, that's not a cheap experiment, but we can make them cheaper. We can actually have another way to look at our universe. We can look not at light. The only thing which we can measure right now is light of different frequencies, X-ray, whatever, but it's still light. We can actually look at have a completely different view of the universe by measuring the different gravitational waves coming from different positions and try to do some, telescopes of gravitational waves. Would be completely wonderful to see what it gives us. All right, sorry for being late, and that's it for today. And if you have any questions, please ask.
Thank you.
2 people didn't sleep.
Mm.
All right. Okay, well, see you on Monday then.
Thank you.